Back to the Piezo Shock Show. This is episode number 13. And today, how do I determine type in a low aspect ratio ceramic sample? As you might already know, we try to design our piezoelectric resonance to highlight a certain mode because we want to isolate that type of operation, either for property characterization. So, for example, we want the thickness to be small and the width to be, or the radial direction or the diameter to be large, so we can isolate a certain mode, so we can utilize that direction of resonance most effectively. So, but what if for practical reasons, you are constrained to develop your ceramic, or you have a ceramic that doesn't have those perfect dimensions, and then obviously it's going to depend on your application whether you have which dimensions are required for your device. And oftentimes the device itself, once you assemble the device in many components, then you do have that uniform method of excitation. Longitudinal, for example, we put a horn on piezo ceramic discs in order to highlight longitudinal or thickness type excitation, whereas perhaps the transducer in itself doesn't have a very high, or the piezo ceramic in itself doesn't have a very high aspect ratio. So let's get going and move toward the question. So the specific question, the person asking had a ceramic which is 8 millimeters in diameter and 3 millimeters in thickness. And the question was, they had a mode at 250 kilohertz that they measured, and they also had a mode at 620 kilohertz. The question is, though, it was obvious to them because the diameter was so large that the first mode was definitely the 250 kilohertz mode. But the second mode was questionable. They were asking, which mode is this? So let's dive in here a little bit and kind of start to understand. So how do we understand these? How do we understand which mode it is, and from a calculation perspective? And so what we use are frequency constants, which are actually derived from material properties, density, compliance. They're so derived from that, but they're also mentioned in material property data sheets. So what I did right now is I just took a soft materials property from a data sheet from the company CTS Noliac. So I took their data sheet and I took their frequency constants, which are in the units of hertz per meter, and I used that to calculate approximately what frequencies those dimensions mentioned earlier in that ceramic sample would give us. So for the planar mode, which is the kind of radial vibration, the parameter was 2,270 hertz per meter. And for the thickness mode, the parameter is 2,067 hertz per meter. So because the length wasn't very, the planar dimension, the diameter isn't very large in comparison to the thickness. So that's kind of makes you closer to slightly edging closer toward a 3-3 resonator, where the thickness is very large, the polarization is very large, and the other aspect ratios are smaller. So it's more like a thin rod with polarization in the thickness, and the kind of thickness, which is also kind of like the length. So it kind of tends toward that. So perhaps the actual frequency constant for this specific sample would be edging closer to the 3-3, but let's just keep going with these calculations. So the first mode, you calculate from 8 millimeters diameter, you divide that by the frequency to the frequency constant, and you get 280 kilohertz. So it kind of matched the 250 that was being reported. For the thickness mode, you divide 2,067 by the thickness, and you get 689 kilohertz. Now, this is obviously an estimation. What the person actually got in practice was 620 kilohertz. This does actually make sense because the thickness was 3 millimeters. It was less than 3 times smaller than the diameter, which is 8 millimeters. So it would make sense that the actual frequency calculated would show lower characteristics, and already the first mode had lower frequencies too. So it could either be that fact that causes the frequencies to be significantly lower, because this is, it was 280 for my calculated value for the For the measured value is 250. So this kind of goes along with that story, both of not having the right aspect ratio, which would perfectly get you in the thickness mode, or it also is the fact that the data sheet values that I got from a kind of random material isn't the same as the material that we're using. So also looking at the planar resonance, the third mode. So when you're doing, so there's two things I want to mention here. All right, there's two things I want to mention. So the way to calculate the second resonance appearing on your impedance trace from the planar mode is going to be approximately 3 times larger. It's not going to be exactly 3 times because the planar mode is not governed by the sine function. It's governed by the Bessel function, which adds some differences, and there's Poisson's ratios in effect. But it's about 3 times larger than the original resonant frequency, and that would lead us to 850, which is much higher than the 620 kilohertz measured in practice. And also the other killer way to really understand, let's say you had such a funny geometry that they actually kind of end up being the predicted resonant frequencies end up being similar. So if the thickness mode, in order to increase its frequency, let's say it was, instead of 3 millimeters, it was 2.5 or 2 millimeters. So now the third resonance, or the second appearing resonance, which is also the third harmonic from the first of the planar mode, is appearing at the same frequency as the thickness mode. So how would you tell the difference if they were close by? The way you could really tell the difference is in the coupling factor. The thickness mode has a significant it has a high coupling factor in comparison to the planar mode. So that would also be a way to indicate where you have more coupling especially for the third planar resonance, or the second appearing one, which is also the third harmonic. That's going to have lower coupling than the first one for sure. So that lower coupling due to the higher mode number versus the original mode number for the thickness mode is going to be significantly different. So you'll see a large dip in impedance. You'll see a farther anti-resonant frequency for the first thickness mode in comparison to the third or second appearing planar mode resonance. All right, so this was it for today. So the answer was, well, okay, let's zoom back out there. The answer was it's the thickness. The thickness mode is active, although it's not a perfectly behaving thickness mode because you have that ratio is not appropriate. 3 millimeters thickness and 8 length or 8 diameter. So it's not the best aspect ratio, but mode shape is going to be more closely related to the thickness mode. How to analyze such a ceramic in this case, and I'll speak a couple more minutes. The best way to analyze ceramics don't have good aspect ratios. One of the good ways to do them is use a laser vibrometer or some type of very precise displacement measurement system where you can apply a voltage and you'll get displacement, and you can measure the displacement in the thickness direction. You can measure the displacement in the axial direction and get the D31, the thickness direction, and get the D33. It's not a thickness mode because it's not resonating in a thickness geometry. It's simply just being excited. And in a DC case, which is always either the 33 or the 31, the planar mode isn't even active in that case as well, because there is not that resonant strain appearing in the device. So I hope this answered the person's question very well. If you have questions yourself, either you can pay $500 for a approximately 1-hour call with me, which may seem expensive, but it actually provides a lot of value to the different companies that provided that 1-hour consultation for their specific device. It's going to be confidential, or simply just post comments, email questions. I will get on the list. I've been already answering some questions. I received this specific question through email. This is day 2. Yesterday, episode number 12, I spoke about kind of a general approach to the question about planar resonators. But today I really hammered the person's question, and I hope it kind of made sense, and they're able to continue forward with their work. I believe the question was from a student. So students and professionals are both equally welcome to send questions through emails or engage in the comments, and I'll also see you what's going on there. All right, take care and see you tomorrow for episode number 14, the 2-week anniversary.